Today we are going to study beats. Non-listening. Can you show me the last video which I shared with you guys? If you have pen, share. I got. Give it. So before I start the beats, I forgot one concept that was the Queen's tube. So Queen's tube actually creates the interference of sound by varying the path difference. So in the design of Queen's tube, we have two types of pipe. One is called the fixed pipe. So we have a fixed pipe. And then the other is called the slider. Slides over the pipe or maybe inside and outside. So what we do is in the tube, we create a hole and exit. So near the hole, we put some sort of, let's say, a tuning fork which will create the wave. The wave will travel inside, but the moment it will enter, it will enter, the wave will actually divide into two parts, one right and other left. Okay. And then we have the slider pipe, that pipe which can slide. So this will change the distance it will travel. Okay. So okay, let me take nice curve part of this some letters. The whole idea is if I call the length as in here as L1, something we can say capital L, and the remaining length has something we can say L dash whatever. So what you can see that the sound will travel right and left. The sound which will travel right has to travel how much? to reach the
L
other end.
plus L plus. Yeah.
Okay, so I need to
So 2L dash plus.
just one. I think I just should take up to opening is one length, another is the. So the right way of doing this way. So till the left and till the opening, the length is fixed. The L is fixed, right? This L is fixed. The only variable is L dash, isn't it? So you will travel on the left side 2L, right? I mean, ignoring the this is H and H is you just ignore. Okay, anyway, you can take H into consideration as well, or you can think as a pi r also. So if you think as a it's a circular, so you can say the left wave will travel
2L
L
plus
plus
5.
plus A. You can say x1 or x left, and the right will travel. It will travel L dash plus pi r plus L dash. Correct?
So plus L plus L is.
No, no. I'm taking L dash from here only,
Um,
from the opening itself. So nothing so easy, na? So the path difference that they will create while reaching this end, where there may be some listener. So the delta x turns out to be x right minus x left, isn't it? And you can clearly see the answer will be how much?
2L dash minus 2L.
Twice L dash minus L. So now let's say for a certain orientation, so the way we solve is like this. So when at L dash equals to L, at L dash equals to L, not L, L1, like when the length is L1, you hear maximum. What does it mean? The delta x must be n lambda, isn't it? So
Yes.
can we write as twice of L1, uh, L L1 minus L equals to n lambda. At L dash equals to L2, you hear next maximum, the consecutive one. Now, what does it mean? 2L2 minus L must equals to n plus 1 lambda, isn't it? Because we are hearing the next one.
Yes.
It is clear? So, between two successive maxima, the the L dash value we wrote as L1 and L2. And if you take a difference of these two equations, you can easily find the lambda. So 2 minus 1 implies what it implies. 2 minus 1 implies 2L2 minus L1 is lambda. So if you know the L dash value at two successive maxima as L1 and L2, then you can easily calculate the lambda of the wave. And because the tuning fork will have the fixed value of frequency, so we can find the velocity of sound by the formula F lambda. Now F is known to us because of the tuning fork, and lambda we calculated for the two successive L1 and L2 values. And this is how exactly you produce the maxima by the those who play the band. So if you have seen the people who like play the band, they have a something like a quince tube. They keep on pulling back and forth. So next time when you are attending some marriage ceremony, and if some band is playing, you can look at closely at the big horn-shaped band. Like they have really big mouths. You might have seen, right? and then they keep on pulling a Queen's tube. So look, I can let me search for the diagram. Anyway, so this you can write as so the velocity of sound is 2f into like this. Let me search for it. Okay, I'm not finding something interesting. Okay. So this is the use of Queen's tube, and this is based on the interference concept. So whenever there is interference, you get the maxima and minima. If L1, L2 represent the one maxima and next minima, in that case the answer will not be this, isn't it? In that case, the answer will come 4 times. Is this clear?
So can you see?
So here I took the L1, L2 as the two consecutive maxima. Now what if I take maxima and minima? So if at L dash equals to L1, you hear maxima or maximum loudness, and at L dash equals to L2, you hear next minima. In that case, the formula will be 2 L1 minus L equals to L lambda, but 2 L2 minus L is not L lambda, it is 2n minus 1 into lambda by 2. Or you can take plus 1, it really doesn't matter. So 2n plus 1, okay, we are taking the next one. So 2n plus 1 lambda. Yeah. Now this is like L lambda plus lambda, isn't it? So now if I take a difference, delta x dash minus delta x, this will give you 2 times of L2 minus L1 is lambda by 2. So lambda in such case will be. So for maxima to maxima, we have 2 times. This is maxima, max to mean, or vice versa. And max to max or mean to mean The answer will be 2 times. So you have to be careful with the language of question that how they interpret the L1 L2. Right? Is this clear? So this was the Queen's tube for you, and it was part of interference. So now we can actually move to the next concept that's called the beats. So beats is also interference of wave, but here the interference occurs at an instant of time. So it's called the temporal interference because it is time bound, not a position bound, which is called the spatial interference. You can also think bits as a temporal interference. Now, human mind, or you can say human ear, can distinguish between two sound notes if the time of arrival of the two sound notes is more than equals to 1 by 10 seconds. So, if this is your ear, and if a sound wave is approaching, let's say a pulse is coming towards you, and the next pulse is also approaching. So, if the two sound notes reaching your ear, if the arrival gap is more than 1 by 10 seconds, you can hear distinctly. Yes, the brain will be confused that it is hearing two sound notes. So for distinction of two sound notes by brain, the arrival time difference should be greater than equals to 1 by 10 seconds. Okay. So inverse of time period we called frequency, and that should be less than equals to 10 hertz. So we can only distinguish between two sound notes if their frequency is less than 10 hertz. So anything more than 10 hertz cannot be understood by the brain, although it is happening. So we say this as beat frequency. We'll learn about this. It's called the beat frequency. So the beat frequency less than 10 hertz we can only hear, and more than that we don't hear. So okay, anyway, what is beat frequency? So first of all, what is beat? It's, it is the phenomena of superposition
Call from India +917.
So it is phenomena of superposition of waves of of slightly different frequency. Understood? So it's a phenomenon of superposition of wave of slightly different frequency, due to which alteration in intensity of sound is observed over time. So you all can play this beats right now. So if you have a mobile phone right now, so you can. Anyone having mobile phone right now?
Yes, sir.
Yes.
You can download something called the frequency generator app. So there is an app which generates frequency. It's freely available on the Play Store. So let's play this beats concept. So you can search frequency generator and let's download. It
Done,
works.
sir.
Okay. So if two guys, if you have done, then one will play some frequencies. You can choose any value. So you can decide that which frequency you want to choose. Let's say you choose maybe uh, like 500 hertz. So author will choose 500 hertz, and the other can choose 501 hertz. And you can play together the sound I will hear, or you can also hear. So first, only one will play. Someone plays this frequency. So switch on, and I think there should be some
So we have to put
methods.
mic on.
Yes, then only I can hear. No?
Okay.
Sure, I'm
So
not able to select 501. 506 is coming.
so okay, but okay, maybe I mean it's difficult, but yeah, 5 and 6 is also okay. That's okay. Now you can play
So
you both can play it together. You start together. When I'll say 1, 2, 3, start. Okay, 1, 2, 3. No, both have to start. It is not running continuously or only one time.
it is continuously running.
Yeah, so I need to hear. Na? Make the like a sound level low, and then switch on. Okay. So much noise. Shut down, shut down. Switch on. Why we have so much background noise? There? You can. So let me take some value. Maybe. Okay, so anyone with 500?
Sir, yes, I'm playing 500.
So let me play. Can you hear what I'm playing? Just this is so much ad. Okay, I'm playing. You also play. Okay, but how it will go like this? Okay, I need to play, but so maybe I need to play two phone together. Okay, just one. I think I can do it. Maybe. Okay, yeah. Is it audible? No. Okay, anyway, so leave it. So the best way is like if you have two mobile phone at home, you can play it together, and then you can see the variation of intensity. So it is easy. It's been done if you have two mobile phone at home. So anyone having two mobile phones? Can I arrange for some time?
Sir, sir, please.
Pardon?
So, please will you repeat? So, what were you asking?
So I'm saying that if you have two mobile phones at home, you can play both the mobile phones together, and you yourself can hear to the variation of intensity. This is what I'm saying. Understood? Am I audible to you guys?
Yes, sir.
Yes, sir. So, yes, sir, it is there. Like, variation is there. If we play 501 and 500, sorry, 506 and 500, then there is.
Yeah. So do you feel the variation? Now you can also see that if you make 500 and 520, then do you feel the variation? Just let me know.
Yes, sir. So, there is variation 520 and 500.
So make it 550, like 500 and 550.
So, but what are we trying to observe here?
For larger difference, the variation cannot be observed. If the two sound notes having very large difference of frequency, the variation cannot be observed periodically. Okay, when I'm saying variation, it means the intensity should suddenly grow very high, and then I can go back to the normal. Is it happening? Anyway, let me do it mathematically. So beat is only possible when we have two sound notes which is vibrating with slightly different frequency. The frequency difference should not be very high. Then only you can observe it. So let's say this is the listener, and we have two sources of sound. Of frequency F1, F2. The sound is arriving like this. Okay. So the first sound which is arriving there may have frequency. So let's say this is x equals to 0. So I'm using the formula y1 equals to a1 sine omega 1t minus kx, and y2 I can take a2 sine omega 2t minus kx. So by the choice of origin at the listener location, the x term will be 0. So at x equals to 0, the formula will look really nice or simple. A1 sine omega t and a2 sine omega 2t. You can also write this as a sine 2 pi f1t 2 pi f2t. Now, mathematically, if I take A1 and A2, then it will be difficult to organize further into some nice relationship. So, for mathematical convenience, we take A1, A2 equal, let's call it A. So, why I wrote first A1, A2? Because you should remember that in beats, the amplitude having no restriction, it could be same, it could be different. The only restriction is about the frequency, which must be different for the two sound notes to produce the concept of beats. So beat is basically like, let's say if you have a table and you are hitting with a maybe a spoon. So if two guys are hitting the table with a spoon, so you are coming and hitting the table at a certain rate, then it is not always true that the moment your spoon will hit, the other spoon will also hit. So it is possible that when you hit, the spoon is in air, and when this will hit, then this spoon is in air. So we will get the intensity of the hit because of the individual spoons. But what if they hit together? At that instant, the intensity will be large. That's called the beats. Guys, give me 5 minutes. So. Hello guys, are you there? Anybody here?
Yes, sir.
So I was trying to, create the logic of beats. So if you're hitting a table with a spoon, so when the first spoon will hit, the second may or may not hit. When second will hit, the first may or may not hit at the same time. So it is quite possible the chance that the two spoons will hit together will be there if they have the definite frequency. It means after some time they will be hitting at the same time, and at that instant the intensity of sound will be high. The same logic we can apply for the beats here in general. That if a two sound wave is coming, so if the maximum of the first wave is reaching at a certain instant, and if the maximum of the other is also reaching at the same instant, at that instant the intensity becomes maximum. Same goes with the minima. If both minima will arrive together, it will be maximum, the minimum. So we need to know how frequently they come together. How frequently means coming together is also one event. So they will come together with the same maxima periodically, and we need to know the difference of the two such instant. So the interval after which the maxima is observed, two consecutive maxima is observed or two consecutive minima is observed, we call it a beat interval, and the inverse of beat interval is called beat frequency. So we define something called beat interval, and we say that it is the duration between two consecutive maxima or minima So it is the duration between two consecutive maxima minima. So beat frequency we define as so let's call it delta t. So beat frequency is defined as inverse of beat interval. That's the logic. So let's do it mathematically. So the first wave is a1 sine 2 pi f1 t. Let's keep it a only. So we are keeping the amplitude same. F1, F2 are not varying much, so they are roughly same. The resultant wave will be the sum of the wave 1 plus 2. We can take a common. We can say So now you can use the sin C plus sin D formula. So sin C plus sin D is how much? 2 sin C plus D by 2 into cos C minus D by 2. Now you can see f1 plus f2 by 2 is the average frequency, which is close to the individual value. So if this is f1, if this is f2, so f1 plus f2 by 2 will be close to this. So this is called the regular frequency. This is called the regular frequency. And the term with the cos is not regular because it is the difference, which is a very small value. So a cos, maybe I can do like this. 2 pi, the difference or 22 here, 2a into sine f average into t. So it seems that this is the regular sine function with a new value of amplitude, and this amplitude we call it a time dependence amplitude.
So the initial part.
Yeah, the initial part is called the time dependence amplitude because this is the regular sine function. You can see this is a sine function. So instead of a, now what we have here, this big thing,
Yes, sir.
this entire thing we call amplitude. And you can see this is the amplitude, which is the time dependence, which is twice a cos uh, 2 pi, and you can call delta f by 2 into t. So we keep it like this only. So the intensity we define as square of amplitude. So the mathematically you can say I will be equals to some constant into 4a square into cos square, the 2 pi into the frequency difference by 2 into t. So I can also write as the resultant intensity of sound will be time dependent, which is 4k a square into cos square into pi delta f t. Let's write like this one. Okay, so this is the entire effort we are trying to put here. So if you remember the scenario of interference in which the intensity depends on initial phase difference. Here the intensity does not depend on the initial phase difference. So for IR max, what we can say? So maximum is possible when this is 1 or minus 1, right? Isn't it? Which means the cost value is either plus 1 or minus 1. And we know that This occurs at m pi, because if m is odd, it will be -1. If m is even, it is +1. So this is a general writing, the solution of this equation, right? So t turns out to be how much? M by delta f. Because time cannot be negative, so we write as m by mod of the difference of frequency. So the first maxima, if I assume at 1 upon this, then second maxima will be 2 upon this, and so on. So the mth maxima will be m by, so m plus 1th maxima will be, and what I said, the beat interval is defined as the difference between two successive maxima. And if you take the difference, you get the 1 upon. And therefore, beat frequency, which we define as the inverse of time interval between two successive maxima or minima, you can choose both. The answer will be abstract. So it is inverse. This will become the just the difference of frequency. That's why the beat frequency is because sorry. So beat frequency we define as the difference between two successive maxima or minima. I did it for the maxima. You can do also for the minima. You get the similar answer. So now you can also say that the delta t, that is the time interval between two successive maxima. So time interval between two successive minima or maxima. So, sorry. So this you can also write as 1 upon the difference of frequency. So if they ask you what is the time interval between one maxima and the next minima, so time interval between one maxima and next minima, the answer will be delta t by 2, right?
Yes, sir.
It's a 2 times of mod of. Now the concept of bit is not just used for this chapter, but in even SHM chapter, this concept is used fairly. In fact, any periodic, motion, you can use the concept of bits. So, for example, if you remember, if I create a question like this, so let's say we have two circles. So it is equivalent to like there are two particles moving with a different amplitude A1, A2. Okay. And the first particle is moving around the circle with angular velocity omega 1, and the second is moving with the angular velocity omega 2. So the question is after what time they will be aligned again. So now after some time it will be here, it will be here. So these two are not aligned. So maybe after some time you are here, it is here, so it are aligned. So the question is when they will align again. So questions like this we can always solve using the concept of beats. So align again means uh, like having two maxima condition. Like when they are aligned again, it means the amplitude is in the same direction. So it's like consecutive interference. You can think that way also. And the answer is pretty simple. The answer is simple. The delta T will be after what time they will align again? So 1 upon difference of frequency. That's it. And frequency you can attach. So omega is 2 pi f. So you cannot f as omega by 2 pi. Okay. So it will be omega 2 minus omega 1 by 2 pi, which is simple answer. 2 pi upon difference of omega, which is even the simple logic we have been solving this question like this only. But the bit frequency gives you the direct answer. So no need to think also. So you may solve a question like a oscillating pendulum question. So if you have a oscillating pendulum, let's say we have two pendulum, and but these pendulums are having different length, so they are not having same length. Just I'm representing.
Yes, sir. Understood.
So now if we have to solve these questions in which we have two pendulum with a different length, L1, L2, and if you release them after tilting sideways, so let's say you move both of them sideways, one is here and the another is somewhere here, and if you release they will not be aligned again, I mean all the time. So the shorter one will move faster because of the small time period, the bigger one will move slower because of the different time period. So when they will be aligned again, so after what time the two string will be again aligned to each other. So again it's the same question, we can all again solve by the same method. So it's 2 pi under root of and now we can find omega. So omega is uh, g by L under root, right? So remember the omega formula. So 2 pi under root and root g we can take common. So 1 by small m minus 1 by L. And so the value wise. So we can solve directly. Like okay, after this time they will align again. That's natural. So many questions we can do like this. For example, if we have a question like this. So let's say there are two roads with a large number of vehicles align. So your vehicles are like a, you can think as a dot. And they're infinite such vehicles. And the gap between each vehicle is g. Okay. And all are moving towards right with some velocity v1. On a parallel road, so now let's say we have the vehicles moving on the two roads. So one is having the less congestion with more gap. Assume the gap is uniform. Other side is less gap and the gap is again uniform. So if I want to know per second how many vehicles will be so the question should be okay. There's a question which I need to bring actually difficult right now. So again, questions like this you can see in kinematics actually. In Olympiad, basically these questions are come, and the way to solve is not kinematics. The way to solve is concept of beats, because it's like time bound superposition. So something like the alignment problem. So they will align themselves, then they will not align, then align, then not align. So questions like this generally appears in kinematics, which is solved using the concept of beats. So beats is a method to solve a large variety problem in which alignment or yeah, that kind of question is only asked actually. So we can also do it for the minima. So IR we got the formula as 4k a square cos square. It's good to write this as I equals to I naught y square like this. So for IR minimum, you can write so minimum is 0. So when cos is 0, when the angle is odd multiple of pi by 2, right? Pi cancel. So you get t equals to hello, are you there, Harshit?
Yeah, sir.
So here m will be you can take from 0, 1, 2, so on. Okay. So now you can say again, if you find the first instance of a minima, you get, let's say, 1 upon this, but the second instance will be the 3 value, 3 times this. So if I just take the delta t using any two, so you'll get the answer, the t2 minus t1, and you can clearly see that it will again come to be the same answer. And so the bit frequency will be inverse of the two minima. So what I'm proving here is that the maxima, two consecutive maxima is also called bits, two consecutive minima is also called bits. Okay. Graphically, it is going to be very interesting. So this is a quite used in communication. So if I write the y resultant formula, it looks like some value, let's say a only. I'm just writing a, or if you want, you can write like this. So the yr turns out to be how much? You can see 2a cos phi. I'm writing like this into sine or if you want to write full, you can write full. So you can see which frequency is high, this or this. So you can see the right is high, right?
Yeah, so
And
plus 1.
left is low because it's a difference. So let's say if I take 100 and 101, the difference is half, but the sum is 100.5, right?
Yeah, so 100.
There is a huge difference. So if a frequency is low, so which function will have bigger time period? The small one or the big one?
Small
So,
one.
yeah, so small frequency means more time period. So if you try to plot a graph like this, so graphically it is really nice. The low frequency will repeat slowly because it will have a high time period, like big time period. So the low frequency signal will be like this. This is the difference of frequency. And it will continue like this. So you might have heard about the FM radio. The FM represents the frequency modulation. Frequency modulation. So similarly, we also have something called AM radio, and that is called the amplitude modulation. So modulation basically means you modify. So the word modulation has come from the word modification. So when you try to modify the amplitude, so if I draw the other way around, so if you plot the graph, the low frequency is oscillating like this. But in the same time, the high frequency signal, which is the regular one, this will oscillate like this. And the low frequency will decide how big the peak will be. So in a way, the high frequency will oscillate in this gap, and you can see that the amplitude of the high frequency signal is getting modified all the time, right? So generally, in case of a regular sine wave, the graph is fixed value like this. So same height everywhere. So what we have done here, we have modified the amplitude, right, as per the low frequency signal. So this is the low frequency, and this is the so this is the graph of very simple graph. You can also plot in a graphing calculator, like you can write as some value cos maybe 2x into sine let's call it 100x. That's simple. If you want to see, you can see this graph. Let me show you. So we have done this in basic math, right?
Yes,
If you
sir.
remember. So cos x into sine 100x. Okay, so you can see clearly. You can see it's a fairly high value. Let me make it less so that you can see first. So if it is 10x, like cos x and 10x, you can see there is, okay, let me draw a separate cos x. So you can see, and then let me draw one more minus cos x. Then you can see something here. So you can see the graph is oscillating between the smaller variation amplitudes, right? If I make it from 10 to 20, you can see it will be more zigzag. If I make it 30, you can see it's more complex. No, if I make it now 40, you can see. So if I make it 90, you can see it's very closely uh, moving in between the two. So the high frequency sound we cannot hear because our limitation is some range of frequency that we can hear from 20 hertz to 20,000 hertz. And this low frequency sound we can actually hear because our voice is only low frequency. So like light wave is we're having very high frequency, and sound is having low frequency. Like normal voice signals are very low frequency signals. In fact, all voice signals are called low frequency, and all electromagnetic signal or wave is called high frequency. So in communication, the sound is superimposed on the high frequency carrier wave, which we call carrier wave, and they carry it forward to a distance, and then we make, by using some sort of filter, we remove the message wave width from the carrier wave. Okay, so that is called the peak detector. There is a device called peak, which only captures the peak value. So let's say if I remove this graph, and this is the only graph, the topmost graph. If I only pick the peak value, so what peak will represent? Which function? The peak of this graph will only represent the cos function.
So why?
Oh, yeah, understood.
Yeah, so because the peak is the cos x function. If I remove this part and if I just go to cos x, see this is only peak value, right?
Yes, sir.
In the other way around, if I just pick the peak value, so there is something called peak detector, and if you plot the peak one, you regenerate the actual voice signal. So what we transmit is not the voice, what we transmit is the electromagnetic signal, but we modify the electromagnetic signal as per the voice signal. So that's called the amplitude modulation, AM waves. So when we do it, when we modify the amplitude, so when during transmission, what we transmit is the light wave only. We don't transmit sound wave at all. But as per the sound wave, we first modify the light wave and then we transmit, because light can move really fast, so it will take no time to reach from one part of the earth to the other part of the earth. If I send the sound, then you can imagine how much time it will take for you to talk to me actually. So I'm saying something or listening right now, isn't it? So over the various channel, like my voice is not going. Actually, what is going is the light wave actually. Okay, electromagnetic wave is reaching, not light. You can say any electromagnetic wave is reaching you, and when the wave is coming to your device, like towards your device through the various propagation channel, so your device is having the method to only collect the peak value. And when you collect the peak value, what you get is the actual sound signal, because that is how we created the modulation. So that's called the demodulator. So you first modify the sound, I mean the light wave as per the input sound wave, and then we transmit. After modification is done, we transmit it. It goes to the air, vacuum or whatever, whatever, and reaches the receiver end, and we demodulate. So the demodulation is the method of picking the peak value and then reconstructing the message. So we reconstruct the message, and then the message is reconverted into the sound using the speaker, like the diaphragm. So the microphone is doing the same job. So earphone is actually the reverse of microphone. So in earphone, what comes is the electrical signal of frequency same as the voice, and then a diaphragm is attached to it, which oscillates and creates the sound sensation. Anyway, so the whole idea of signal transmission is all about the amplitude modulation. So this idea of modulation is very, very important, and we cannot transmit sound over the long distance because of the issue of, there are variety of issues, like issue of degradation, issue of noise. So we have nowadays device which is called noise cancellation devices, and or technology actually. So what they do is, again, they use the concept of interference, and they internally generate the sound which is out of phase with the noise signal, because every noise will have some characteristic frequency. So what we say and what we get the noise, they will have a difference of frequency, and this is broadly studied by the machine actually, and they are able to create the sound which can cancel the effect. And so what you hear is only the sound which you are intended to actually hear. So the concept of interference or beats and everything else is used extensively at a machine level actually. Now we are not doing it manually, definitely. So the idea of these things are important. Like you should know that how signal is propagating through the space, how we receive. So definitely we are not receiving any sound. My sound is only till my device. After that, there is no sound. Now there's something called the reconstruction of sound. So we recreate it using the concept of, like, peak detector and all. Okay, so I hope this is clear. So at home we have something called the Wi-Fi modem, routers, and so on. So modem is basically stand for the modulator and demodulator. So while giving you the signal, it demodulates, and while sending, it will modulate. Understood? So let's say I'm using the Zoom application to teach you guys. So whatever I'm saying is actually converted into some current, and that current becomes the message signal. The message signal actually creates the electromagnetic signal. So of course our device is radiating the signal, and the signal is picked by the Wi-Fi. The Wi-Fi sends to the nearest I mean the service provider, which is having the big antennas which transmits over the range, which receives the other part of the world. Again, they also have their antenna. They receive there, and they do the the reverse process or reverse engineering to recreate what I said. And imagine these things are happening at a scale which brain is not able to understand. The reason is there is a delay, but for the delay the brain is not bothered about. But for the light, because the speed is 3 × 10⁸, see in 1 second it can travel 1 lakh kilometers. So to travel even few thousand kilometers, it takes just a fraction of a second, and that delay is not perceived by the brain. So that's why it's called the live broadcast. So nothing can be live, to be very honest, because the process will take some time. But all the devices work at a frequency which is of nanosecond scale, and these works gets completed in few nanoseconds. So on a nanosecond scale, it's a quite a big process. So it may take 100 nanosecond, maybe 200 nanosecond, maybe like a thousand, not thousand, maybe like, yeah, 1,000 nanosecond is also possible. So on a nanosecond scale, these are very delayed process. But for brain, this delay is of no use. The whole idea of speed is all about brain. So when we use computer to do something, or we make sure that the computer will do it in the less than the normal perception of brain. Like we perceive very fast, like 0.1 second we perceive. So if I finish some task in less than 0.1 second, you will be happy because you will not realize the delay process. But for machine, that is enough time to do millions and millions and millions of computation. So when you play a video game, then the machine is actually delayed response. It is doing millions of trillions of calculation, and then after that, you get the output, and then you realize that okay, you're playing it live and natural. So things are there. Anyway, coming back to the theory part. You can see that how the signal is modified. So the actual, this is the actual signal. So if you look carefully, this is the actual signal. Because this is having roughly same frequency as that of the individual source. This is called the modulation part. So we are modulating the actual signal, and modulation is time dependent. And what we are modulating is the amplitude part. So A is getting modified with time. So you can also call this as amplitude modulation. So bit is also one example of amplitude modulation, and that's why the regular sound is no longer regular. You can see these are the point of minima, these are points of maximum. So the interval, the beat frequency is basically what is the beat frequency? This interval is called the beat interval, or you can take from minima to minima. So this we call beat interval. You should know how to read the graph also. So this is called beat interval. So by graphically, if they give a question which is graphical in nature, you can just read it. And so the beat frequency is this one, graphic. Understood? Okay, this diagram is not correct because this is actually I have drawn for the cosine function. No, this is fine. Yeah, cos. This should be sine function actually. Yeah, so I think. Yeah, there. I have just done opposite. So any nevertheless. So instead of cos function, I have done for the sine function. So this is basically what I have done is for the sine x and sine kind of 100x or 10x, because I have started from the mean position. If I just shift this arrow, it just become true answer. So, yeah, I can leave like this. Now this is correct. Okay. Or shall I keep it over? That's nice. So I hope this is clear. This part is clear. So this is the beats for you. And now comes the concept of Doppler effect. So the concept of beats we use for the Doppler effect problems actually. So what is Doppler effect? It's very famous. So if you go to the local, I mean, the railway station or any local train, so the moment the train is approaching you, the intensity suddenly grows very high, and the moment it crosses you, the suddenly the sound intensity drops very quickly, right? So due to the relative motion of source creating frequency and the observer listening to the frequency, the relative motion creates an impact which is called the variation of sound or variation of frequency. So the variation of intensity due to the relative motion of source and observer.
170217852.
So the variation of frequency observed by the listener due to the relative motion between the listener and the source, we call it Doppler effect. Okay. So let me define it. So the variation in observed frequency due to so the variation in observed frequency due to relative motion of source and listener is called Doppler's effect. Okay. So Doppler effect is the variation part. The variation in observed frequency due to the relative motion of source and listener. So that's very important. Source and listener. Like who is creating it and who is listening to it. So the relative motion will decide what you hear, then what is emitted by the source. So there are two effects which we need to know. The first is called effect of motion of source, and the second is effect of motion of listener. Now, why I use the word observer? Because Doppler effect can also be used for the light, not only for sound. So it is for light as well as sound. So let's see the first effect, which is called the source effect. So if we have a source, and if the source is at rest, it will emit the sound in all directions, and the emitted signal will move readily outward from the source, and hence creating the spherical wave front. What we call is wave front. We'll come to that in the other chapter. So these are called spherical wave front. Spherical So wavefront is basically the locus of point at which all waves oscillate in same phase. So the one which has left in the very beginning will be here, and they will occupy the entire sphere everywhere. So all the wave at every point which we collect on the one sphere will represent one phase. So they belong to one generation, you can think of, because they have been born at the same time, or you can say they have been emitted by the source at the same time. So a wavefront is one generation. Each wavefront represents a different generation. Understood? So it's all about generation. So the whole idea is, if the source is at rest, the wavefront will be symmetrical and concentric. Okay, you can think the wavefront as the crest. So the crest will be having distance between them, and the distance between the two crests is called lambda. So you can see lambda in all directions will be same. So it will have the same wavelength. Now, the effect of source motion. The moment source starts moving, the wavefront cannot be concentric. Why? So let's say, imagine the first wavefront was emitted when it was here. So after some time t, the wavefront has grown this much big. Now this is with respect to the source when the source was there. So when you emit, the source was here, and you're moving forward. By the time you emit the second wave, you are here actually. So your sound which will be having emitted will have the new center. So you can see that the new center will decide the new sound. Then after some time you will be again moving forward. So you can see that the sound will be kind of, the wavefront is like coming closer on the right side. Let me do it better way. So for a moving source, if a source is in motion, the wavefront which we generate will no longer be concentric. Rather, they will have a gap like this. So, so the source is in motion. So let's say source is here as of now, or maybe slightly more ahead. Source is here, and if I draw the line of motion towards right like this, there is something interesting you can observe here. And what is that? Now the two crests on the right side having the minimum separation.
So your voice was cracking.
Just audible now? Am I audible?
So yeah, so now it is better.
Once again. Am I audible now? Am I audible? Hello, hello, hello.
Yes.
Am I audible?
Yes, sir.
So now you can see as an effect of motion of source towards the right, the gap between the two wavefront has decreased significantly. And not only that, the wavelength will vary in all directions. So this direction will have different value. So between the minimum, in the direction of motion, it will have the least value, and in the direction opposite to motion, it will have the bigger value or biggest value of the lambda. In fact, lambda will vary from angle to angle. So for every angle, there is one lambda. So lambda will keep on changing as you move. I mean, as you point towards a different direction. So what we can observe that the motion of source actually affect the wavelength. So depending upon the location of listener, so assume that I have a listener on this location, or some other listener at this location, and some other listener at maybe at this location. All will receive different wavelength per second. So listener 1, listener 2, and listener 3 all will receive the different wavelength. And you can see who is going to receive the least number of wavelengths. And the answer is L3. Sorry, least, I mean the smallest wavelength, L3. And who will receive the biggest wavelength? L1. Am I audible?
Yes, sir.
So the biggest wavelength will be received by L1 and the smallest by L3. Understood?
Yes, sir.
In between by L2. So as a result of motion of, so we know the formula that the frequency is written as V by lambda. Understood? So we say that observed frequency will be V. So sound velocity is same in all directions, but lambda is changing. So we can say lambda apparent. So the lambda that we receive from the actual value, now we call it apparent lambda. So apparently lambda has changed for the given observed. So we can understand one thing, that lambda is not a constant quantity. Lambda depends on motion of source. And the motion of source will affect the lambda value from one direction to other direction. You can see on the left side, when source is not moving, when source is at rest, then lambda is not changing in any direction. So it is same in all directions, isn't it? So in that case, if we have a listener in any location, it will receive the same lambda as it is given by the source. And therefore, there is no change in the observed frequency from the actual frequency which is being emitted by the source. So source will emit something and the listener will listen exactly what it emits. But the motion will change the entire calculation. So what is the takeaway here? That motion of source changes lambda. That's it. So that's a one-liner. I will put it here. So motion of source affects lambda. It is clear?
Yes.
Similarly, we would like to know the concept of motion of listener. So it says source is fixed. So source is not changing anything. So the nature of wavelength will be same in all directions. So source will create the concentric wave fronts. Now imagine that a listener is approaching towards the source. So listener is moving towards the source. We call it a V observer. So now the observer is going toward the source. Now I can keep on drawing the wavelengths like this. Really bad, so it's difficult to draw all the, but you can understand. We can extend this diagram further and further. Yeah, this is good enough. So what is happening as a result of motion of a listener? So assuming that these are like frequency emitted by the source. Let's say the frequency of source is f. So how many wave of crest it will receive per second if it is not moving? So when the listener is not moving, then it will receive the same number of wave as that is being emitted by the source per second, right? Understood. But what will happen as a motion of source? So when you move, you receive some extra wavelength, which is part of the medium. Understood?
So not understood.
Yeah.
So why we strong?
So imagine this is like a laddu, and these laddus are moving towards you. This is your mouth. So how much laddu you can eat per second? If I'm throwing f laddu per second. So if you don't move, how much laddu will enter your mouth? F.
Yes, sir.
Now let's say this starts moving further. So in the same time, you will be here actually. So apart from f laddu, you can eat these three extra laddu, no? Understood?
Yeah, sir. Yeah, understood.
No, you're not. Because of the motion, you receive more waves per second. So let's say it's a common sense. Let's say, I mean, there is a like a car, again the same car is going like this. And you're standing on the car. So how many cars is crossing you per second? Maybe 10 or 20, whatever. Okay. So let's say per minute, 10 cars is crossing you. But if you move slightly ahead in the same time, you will get 12 cars, isn't it? If you move slightly ahead, you get more cars. No? So if you also start moving towards the source, you will cross more car than before or same car. Like if a source is emitting a frequency f, and if you move towards the source, so will you receive more frequency or less frequency? You can think frequency as one crest mentally. That mental picture will help you. Am I audible?
Yes, sir.
So as a motion of as you move towards the source, you will actually start receiving more wave fronts or more crest or more wave actually. So what is frequency? Number of wave emitted per second or wave received per second, isn't it?
But
Hello. Do you realize this? Hello. Okay. So the motion of listener or the observer actually increases the number of wave which you receive per second, or you can say it will affect the number of wave which you receive per second. It may decrease also if you go away. So the key takeaway here is motion of listener alters the so when source and observer both will start moving, then both gets affected. One is the wavelength and other is the number of wave received per second. So all calculation that we are going to perform will be in accordance with these two changes. So we'll see how to create the the apparent frequency. So what we are going to do is we are going to do the calculation of apparent frequency. And there are multiple situations which will take care. So first of all, 1D motion. So the source and listener will be moving in the same line. Then we analyze the system. When so when the motion of source and observer is along the line joining them. Okay. So I will not write the case that you can understand from the situation. So case one is when source is moving and the observer is at rest. We will take the velocity of sound as v, and in all calculation the medium will be assumed at rest. Because the velocity of sound which we have derived is with respect to medium, right? In air, we don't derive in ground. So the velocity of sound or any wave, any mechanical wave is always with respect to medium. So V represents velocity of sound with respect to medium, not ground. So all calculation about the velocity of sound is only for the medium frame, which may be water, which may be air, which may be glass, whatever. And because I'm assuming medium is not moving, so it will translate into velocity of sound with respect to ground also. But this is not always the case. So we don't take ground at all. We take medium. Medium may be at rest, maybe in motion. That's a different thing altogether. So when you say wind, wind is nothing but the motion of medium. So if there is a wind velocity, it means the medium is in motion. And if the wind is towards the listener, the medium will come to you. So the sound will, sound will reach you faster. And if the wind is moving away, then sound will travel towards you, but the medium will carry it left or right, and so it may take a different time to reach you. So velocity of wind will affect the velocity of sound with respect to ground, but not with respect to medium. So with respect to medium, the velocity of sound is same in all directions. With respect to ground, it may change because of the motion of the medium. So again, if you want, you can put into words. So velocity of sound will be same with respect to medium in all directions. But it may change with respect to ground for a given direction. Okay. So when medium is in motion, then the velocity of sound in the ground can be changed. So we'll come to that also. So generally, the source will emit energy in all directions or wave in all directions, but we'll consider only that motion which is happening towards the observer. So we only consider the case or the wave which is moving towards the observer. Now here the source is moving. So let's say the source emits the first wave, and the wave travels some distance. Okay. So tell me, in time t, how much it will travel? The wave will travel how much? So velocity of sound in medium is constant, so it will travel v into t. And why am I multiplying by
Time t.
time t?
Yeah.
Multiplying by time t because the next wave will come after time t, not now, isn't it? But because of the by virtue of motion of the source, in the same time, the source will not be here, right? So you can see clearly the peak has reached here, but the source has also moved forward, isn't it? So now while the source will emit the next peak after time t, the source is here and the first peak is here. So you can see the source has traveled a distance of Vs into t, and the separation between the two peaks has changed now, which we call lambda dash or apparent lambda. So can you tell me what is lambda dash here? What is lambda dash? It is Vt minus Vst, which is obvious. So it's V minus Vs into t. So if I make the Vs 0, you can see it is the actual wavelength that we expect, but the motion will actually decrease the wavelength because the observer is towards right and we are moving also towards right. So the apparent frequency that the observer will receive will be the velocity of sound upon the lambda dash. The lambda will change. And therefore, the apparent frequency will be V minus Vs into t. Inverse of time period is called the actual frequency of source. So frequency of source is called 1 by t, where t is a time period. So therefore, this we can write as V upon V minus Vs into F. You can see the answer is very logical and simple. So what is the apparent frequency observed by the listener? The answer is V upon V minus Vs. Now V is the velocity of sound and Vs is the velocity of source. Is this clear?
Yes.
The next
So that V minus,
yeah, tell me.
so that VT minus VST is that from point S where the source, like from the source to
This is the first peak. This is the second peak. So what is the definition of wavelength? The separation between two consecutive crests. So the separation between two consecutive crests or trough is called wavelength. So I am using that concept here. So what is the separation between the two consecutive crests? Will it be VT or will it be less?
so let's.
So that is what we are calculating here, no? Because source is moving forward. So while emitting the next crest, it will be closer to the first crest than actual, isn't it?
Yes.
Because if the source is not moving, the first crest and second crest will be exactly at a separation VT only, isn't it? Okay. So now case 2 will be the listener is still not moving, but source is now receding away. So it's trying to go this way. Now the direction of sound wave we always assume towards the listener. So that is what will matter. So now when the first peak will be here after time t, so at t equals to 0, the source was here, and this is the separation. I mean, this is t equals to t. But in the same time, the source will move towards left. And the distance it will travel is, and the distance the first crest will travel is v into t. So the next crest will emitted here, and you can clearly see that the lambda dash will be how much now? The sum of so lambda dash is how much? T plus Vs into T. So the apparent frequency will be V by lambda dash, and the answer is. So similarly, we can derive all other formula. I'll go to the next page. So now the case 3. So now when the observer is moving, the apparent frequency lambda will not change. So lambda remains same. The source is not in motion, so lambda will be same in all directions, right? So in this case, the lambda dash will be lambda. So what about the f dash? So in a normal situation, when the observer is also not moving, the frequency which you receive per second is f. But because you are in motion, so in 1 second you will travel how much? In 1 second you will travel v naught into 1, right? So how many extra wavelength you receive? What is the gain in wavelength? Gain in frequency, like number of wave which you receive extra. How many extra frequency you receive? So the delta, if we write as distance traveled in 1 second upon wavelength apparent. That's the definition. It may plus, it may minus. Because you are moving towards the source, you will receive extra value. And that is why the apparent frequency in this case will be a plus v naught into 1 upon lambda. Because lambda dash is lambda in this case. Luckily, we have this answer. So, what is lambda? The answer is Vp. Therefore, the f dash, let's call it question 2 and question 1. So 1 and 2 will give you f dash equals to f plus velocity of observer upon Vt. But 1 by t we can call as f only. So f dash equals to, you can see the answer is f into v plus v naught upon. That's a long derivation. And we are doing everything from basic. This is called the extra wave received in 1 second. So frequency is number of wave which you receive per second. You can take the case 4 also. Source is rest and observer is receding away. So, and these questions are similar to the question of, if you remember that Which question? In center mass, we were doing the variable mass system in which there was a water jet hitting the wall. If the wall is stationary, then you will receive the water at a rate of velocity of the water itself, the water jet. But if the wall starts moving, you receive less or more water per second, right? So that's the whole idea, same idea. So if I draw a hypothetical wall, then number of wave crossing this wall per second will be f. But if you move from there, you will miss these many waves which could have passed you actually in the same time. Understood what I'm trying to explain? So motion of the observer will either hit or miss the. So either you receive more or you receive less than expected. So I can say the apparent frequency will be close to how much? The actual no minus the delta f. So I'll write directly so f minus v naught by lambda, which is f minus v naught by vt. F dash is f minus so f dash equals to f into v minus v naught by v. Okay, so you can see something. There is a pattern. If you observe carefully, there is a pattern. Now the situation will be like this. So at the end of this discussion, I'll give you the shortcut trick to remember every formula at once. But these are the basic methods which helps us in solving more conceptual question of like J advanced and Olympiad level. But most of the question can you solve just by a simple trick, which I'll give you eventually. So let's say we have a case 5, observer and listener. I mean, sorry, source and observer both are moving towards each other. So lambda dash will change from lambda. Okay, so lambda dash will be having different value. So it is not equals to lambda. So now it will have value. So the value we can decide by the direction of motion of source. So is source moving towards observer? The answer is yes. It will be smaller. So it will be you can write like this: V minus Vs into T. That's simple. If source is moving towards observer, it will be minus. That's simple. Now, is the observer moving towards the source? The answer is yes. So it will receive more. How much? F plus delta F. But delta F will be how much? So in this case, there is a small change. Here we take the relative motion, not the absolute motion. So we, in 1 second, how much they come closer? The answer is Vs plus V naught into 1 upon the lambda dash. So when the source moves and the observer, we always take the relative motion. So how much they come closer. So with respect to source, the observer has come closer by this value. So it will receive these many extra values. So these are individual calculations. You can see these calculations are very complex. So knowing each term is very important. If I just give you formula, you cannot find the intermediate question. So if I ask you calculate delta F, you will get confused what to do. Because you know only the overall formula, not the intermediate formulas, right? So now the F dash will be equals to F plus Vs plus V naught upon Vs minus V minus Vs. Yeah. Into T. Okay. So we got the answer as F plus you can take F common. So what we get 1 plus and if you take LCM and so Vs will cancel out, what we get is V plus V naught. That's a very famous answer. So the apparent frequency will be F into the summation of velocity in the numerator and the difference in the denominator, like this. Okay. Now, if I ask you to find delta F from this formula, then it's difficult to find. Okay, that's how the intermediate value, I mean, of calculation will be helpful for the challenging problems, not for the regular problems. Like if you want to solve AC or the regular question of JEE Mains and advanced, not all questions, but most of the question you can solve by the formula itself. But if you want to solve the very complex question in which the questions are asking something extra, like how much extra wave it will receive per second and so on, then this method will help. Understood?
Yes, sir.
Similarly, you can analyze the case 6, in which they move away from each other. So observer and source both are trying to like go away from. So if you derive similarly, which I will leave as a homework, it will just reverse the sign. Yes. So it is like V naught has become minus V naught and V has become minus V. So if you do the reversal of the sign, the formula will, you can get direct. So of course you need to derive it from basic, which is I'm leaving as a homework. So if I include all cases, now this one case is also important. Let's say, what if both are moving together? Source is moving towards and observer is also going like this. So because source is trying to approach the observer, the lambda dash will be difference one. And because the observer is trying to escape, so the number of wavelengths will be, so delta V will be like if it is, let's say if the V naught is bigger than Vs. So if V naught is bigger than Vs, you will receive less. If Vs is bigger than V naught, you will receive. So again, it depends on how you consider it. But I can say something that let situation, just take a situation. If Vs exceed V naught, then this is the case of approach. So delta F will be positive. So you will just, so the F dash will be F plus delta F. Let V naught is Vs, receding case, F dash will be F minus delta F. But the delta F will be defined differently in both cases. So in this case, the delta F means, because you're approaching, so Vs minus V naught, the relative velocity upon lambda dash. But in this case, receding, so delta F is V naught minus Vs. And if you substitute any of the formula, you get the same answer, because the change of sign is change of position of V naught and Vs. So it will give you the same answer. So you can say F dash equals to, choose anyone, whatever you want to choose. So the F dash will be So I'm substituting the value everything at once. Just in case you're getting confused why I'm writing like this. So are you there? Hello, hello.
Yes, sir.
Okay, I thought you were not there. So you understood this part?
Yes, sir.
All right.
So I want to see the last thing.
Okay.
Yeah, so done. So this one was for the like for
This is when both
extra
sorry,
1%.
pardon?
Yes.
All right. So if I combine all the formulas together, then f dash you can write it at one go as, so the source always comes in the denominator and the observer is in the numerator, and it's always easy to remember. So observer will be like high priority, so numerator, and source will be low priority. So now to take any situation and try to create the answer or formula. Let's say now in this case the frequency should be high or low. So if they approach, the frequency should be maximum, isn't it?
Yes, sir.
So the numerator should be plus or minus to maximize the frequency. The numerator should be plus or minus,
Plus. Yeah.
and the denominator should be plus
Negative.
or minus. See, that's the answer. You take any situation, they go away. So now this is the minimum case. So numerator should be negative and denominator plus. Let's say only source is moving, observer not. Now VO is 0 now. The numerator becomes only V, and because it is coming towards O, it should increase or decrease. The apparent should increase. So to increase the apparent, the denominator should have plus or minus sign. So V naught is 0, so the numerator will be only V. In the denominator, we have two choices, plus or minus. But we would like to increase the frequency because the source is approaching. So what sign is suitable here, plus or minus? Is this clear, this part?
Yes, sir. Negative.
So similarly, by simple logic, you can understand which term should come, which term should go, should it be plus or minus. You can actually do this manipulation. So in a worst case scenario, when you don't realize the answer, the method, at least you can use this. Else, you can do it from the basic, the way I did. Just okay. So now we have to study the effect of wind. So if we have the wind towards the observer, so if this is the observer, if the wind is moving towards the observer, the velocity of sound we have to replace by V plus VW, because now sound will reach the observer faster, because the V is always with respect to wind. Wind is also coming towards you. So the rate at which the sound is coming towards you is now V plus VW. It is clear? If this is the observer and wind is away from the observer, replace V by V minus VW. Don't worry that VW cannot exceed V. V is 340 meter per second, and we can't have the wind at that speed, as everyone will be destroyed anyway. So V is V minus VW, and that's how we replace. So the F dash will have the formula F into V plus minus VW, which we can put as a single bracket, plus minus V naught, V plus minus VW, That's it. So you can either substitute V plus VW in numerator and in the denominator at the same time. It cannot be plus minus alternatively. Both will be either plus, both will be either minus. And this part depends on the situation, which you can understand how to eliminate. So that's very easy. You can do this. And a third scenario you can also take if the wind is kind of moving at some angle, theta, then V should be replaced by V plus VW cos theta. That's just in case if you want to make it even more general. So F dash will be F into V plus minus VW cos theta plus minus V naught upon and then we are left with 2D motion when they are not in the line. So when the line of motion is different, so maybe you have a source moving in this direction. I'm just keeping it simple. And at the time of emission of the sound, which will eventually reach the observer, the observer is here moving towards this direction V naught. And this alpha is this is beta. I'm not saying these are parallel. This could be different line. It could be parallel also. So I'm taking a general value alpha and beta. So the sound that the source will emit, which will be heard by the observer. So we always take the angle alpha beta at that instant when the sound was emitted, not when the sound is heard. Okay. So if you're listening to sound now, then the source must have emitted sometime before which you will now receive. So the diagram which we plot is something like this, and therefore I'll give you one example to understand this better. The F dash we can write easily by just resolving the velocity vector. So it will be F into, I'm not taking the wind in this case. So let's say the wind is 0. Medium is not moving. So it will be V plus minus VO cos beta. So we always take the approach and separation, not the relative velocity. We take at what rate they are coming upon. That's it. So we take the component which matters for the Doppler effect. The Doppler effect is only due to the component along the line journey. So the perpendicular component will not affect the Doppler. I mean, will not create any Doppler effect. That is what you can say actually. You can say, you can see clearly that the source and observer are approaching in terms of this component. So in this case, you can write, of course, plus in the numerator and the minus in the denominator. But I'm just writing in general. It's going to be any relation. Understand? So let's say there's a very famous example of the train example. This is from SC Verma only. These are two parallel tracks. And the question is, when the train emitting sound and the listener are facing each other, then what is the apparent frequency heard by the observer? So what is the apparent frequency heard by the observer when source and observer are closest, because that's the only case which means perpendicular. The idea is now the source is listening to some sound. The sound the train or this rail or the source will create right now, it will take some time to reach here, and by that time the source, the observer will be here. So now if you're listening to some sound, then I can say for sure the source must be somewhere behind, and source must have emitted a sound in this direction, which took some time to travel, and by the time the sound arrived at this location, the source was luckily present, the observer was luckily present there, and in the same time the source was able to travel till this point. So if you're listening right now something, it means the sound was emitted some time back, which took some time to reach you. So if the speed of sound is v, so in time t, if you travel from here to here, in the same time the sound must have traveled from there to there. That's why the event occurred simultaneously. And this logic will give you the angle theta. You can easily find the cos theta. So you can find the cos theta equals to how much? Can we write Vs by V, no? Right. Now, okay, let's say the observer is stationary. That is the question actually. So observer is not moving. So it is permanently here. This makes things very easy for you, because that's the actual question. So observer is stationary. So at the time that observer is here listening something, it will listen to the sound which was emitted some time back, and the time taken by the sound to travel from the source to the observer is exactly the same time in which the source travel from the initial position to the present position, which is closest to the position. So now if I want to write the f dash, it's very easy to write, because we have the formula what? F into v plus minus v observer, which is 0, correct? Upon what is the velocity of source towards the observer at the instant of emitting a sound. So the source is approaching towards the observer at what speed? It's not Vs, it is Vs cos theta. So can we write like this? Is this part clear? And we just
Yes,
learned that
understood.
the cos theta we can write as Vs upon V from here. Therefore, the f dash will be f into V square by V square minus Vs square. It is clear? So this is the two-dimensional problem that you will come across. Now this is the last problem, which is the last problem of SC Varma. My problem number 89 SC. I think there are 89 questions in sound chapter, right? You can check. I don't have. So it's called the accelerating source. And through this example, I will demonstrate the third method of solving problem. So in this case, the listener is stationary. And the source is accelerating with some acceleration. It starts with 0. So it will emit some sound. Let's say the D is the separation. So the first sound which will be emitted by the source will take how much time to reach the observer? So if I say the emission of the first peak as t equals to 0, so this sound will travel with velocity of sound v to reach the observer. So time taken by the sound node to reach the ear of the observer is d by v, isn't it?
Yes, sir.
Now the next sound note will be emitted by the source after time t equals to t. It will emit the next peak, and because it is accelerating with acceleration a, it will travel half at square. Now the distance left is d minus half at square. So now the second sound which you emit now will take how much time to reach the observer? The answer is t plus, because we are calculating from the beginning. So t already spent to travel, and then the distance left between the two will be traveled by the. So between two consecutive sound note, what is the time interval? Answer is t2 minus t1. So this is called the time interval between two successive sound note to be heard by the listener. And if you take the difference, something interesting happens. The answer has nothing to do with the D, right? The D gets cancelled out. So you get T minus A2 is equal by 2V. Is this clear?
Yes.
So the beat frequency, not yeah, apparent frequency, not beat. Apparent frequency we define as inverse of time interval between two successive notes. So 1 by the answer is 2V upon 2VT minus AT. And you can also write in a fancy way like 2V. You can take T common or a T square common. It will become 2V by T minus A. And why I did this? Because 1 by T square becomes F square, so this is 2V F square. So this is the last answer of the last question of experiment, and this is the last page of the Zoom. I cannot write further, and this is the last topic that I will discuss today. So with this question, we complete almost 98% of the syllabus. 2% is only left, which I will cover in the next lecture. Okay.
Sir, from Wave, right?
Yeah. Wave and sound both.
Oh, yeah, sir.
Wave chapter and sound chapter, including, we have completed 98%. The only concept left is called reflection and some question of beat. So the question from the beat will solve and reflection will solve, which is from the wave chapter. Okay. Anyway, reflection is for every, not only wave and string, it is for both. All right.